Good morning to one and all. My name is C. Soit and I'm from ECD section, roll number 4J8. My topic of the concept video is the temporal computing with superconductors. Introduction. Superconductor electronics after the potential to perform computations at tremendous speeds and energy savings, especially on large scales. Unfortunately, a semantic gap exists between the level driven logic, which CMOS designs accept as a foundation, and the pulse driven logic naturally supported by the most compelling superconducting techniques. So here we can see that, however, superconducting electronics have grown, and with tremendous speeds and energy savings, computers are emerged. Uh, Even though, unfortunately, um, there exists a uh, gap between the level driven logic, which CMOS designs accept as a foundation, and a pulse driven logic, which are naturally supported by the most compelling superconducting technologies. This gap creates a variety of challenges across the full hardware stack, from the circuits up through the CAD and architecture levels. So we can say that we have some disadvantages because of this gap, because this gap creating a variety of challenges across the full hardware stack, from the circuits up through the CAD and architecture levels. Now, what is the supercomputing temporal architecture? Realizing temporal operations in superconducting, the way in which events are encoded plays a critical role in selecting the hardware that most efficiently implements logic operators. For example, in CMOS, in which under race logic, temporal events are represented by rising edges. So we can say that in CMOS, temporal events are represented by the edges with the rising. FA and LA functions are realized with a single or an AND gate respectively. An important property of edge-based event encoding is that it automatically keeps track of the input state at all times. A signal that has made a transition from a low to a high state will not make a transition back to low in the same computation. Temporal computing. This feature breaks down though when dealing with pulses as discussed in section 2. Supercomputing technologies encode digital data as SFU voltage pulses. Pulses naturally return back to their low state, preventing downstream nodes from implicitly knowing the state of its predecessors. Whereas we in the previous slide we have known that it wouldn't come to the low state and or go to the high state easily. That is an important property. Signal that has made a transition from a low to a high state will not make a transition back to low in the same computation. Where here we can see that pulses naturally return back to their low state, preventing the downstream node from implicitly knowing the state of its predecessor. That is how temporal computing is used for us, where the signal comes back naturally to its low state after it going to the high state, by preventing the downstream nodes from the implicitly knowing the state of its predecessor. A potential solution to this problem is to embed the state into each gate. Interestingly, the majority of superconducting single flux quantum, that is SFQ, elementary cells have both logic and storage abilities. Thus, they can be thought of as simple state machines. To facilitate the mapping between our temporal operations and existing stateful SFQ elements, we draw FA, LA, D, and IS as medium machines. Following this representation, we build FA with a merge and a destructive readout DRO cell LA with a C element cell D with a sequence of Josephson transmission lines, that is JTL, and IS with an inverted cell. The length of the JTL chain depends on the selected time difference. In contrast to the other shown cells, JTLs do not hold state. Thus, More than one SFQ pulses can propagate through a JTL chain concurrently. To highlight this difference, we color the init node in the TC Pi Mealy machine gray. Self-clocked temporal SFQ circuits. In contrast to more traditional superconducting approaches where each gate is synchronous and fine-grained clocking is necessary, the proposed scheme relies on asynchronous operations. That is, even in the cases of FA and is where synchronous cells are used, a data signal is routed to their clock port. However, the use of synchronous components may sometimes be beneficial. For example, although confidence which gets satisfied if and only if both phi and phi arrive within the same interval can be built from the above described operations. A more efficient implementation is possible. All that is needed for its realization is a synchronous AND gate. Thank you.